So welcome you all. In the previous class we have discussed refraction at a spherical surface, refraction at a spherical surface and refraction by a lens. So in the first topic we have derived formula for curved surface, that is n2 by v minus n1 by u is equals to n2 minus n1 by r. In this topic we have derived lens formula, that is 1 by f minus 1 by f is equals to 1 by v minus 1 by u, and also we have derived lens makers formula, that is 1 by f is equals to n to 1 minus n to n minus 1 into 1 by r1 minus 1 by r2. This is a lens makers formula. Okay, by using this curved formula for curved surface we have derived these two equations, two formulae. So in this class we are going to discuss power of a lens. Okay, so what is the power of a lens? So here the power of a lens, it is a measure of convergence or divergence of a lens. It is a measure of convergence. It is a measure of convergence or divergence of a lens. Convergence or divergence of a lens. Divergence of a lens. Okay, look at this picture. So I'm representing two convex lenses here. One is thin and another is thicker convex lens. So here the focal length is small, large. Here the focal length is small. Look at the parallel beam of light. When parallel beam of light passes through this thin convex lens, after refraction, so they are meeting at a point on the principal axis. If we take a thick convex lens whose focal length is small, the amount of bending is different, the amount of convergence is different. So this amount of convergence represented by one physical quantity, that is a power of a lens, power represented by letter P. How much the light bends here, the amount of bending is different for different lenses. It depends upon the focal length. Okay, so it is inversely proportional to focal length. Look at this picture. Here the converging power is small since the focal length is large. Here the converging power is more since the focal length is small. So we can say that refracting power is equals to the reciprocal of the focal length of the lens. We'll derive this expression in this class. Okay, this is nothing but the power of a lens. It is nothing but measure of convergence or divergence of a lens. In case of a convex lens, the light converges. In case of a concave lens, the light diverges. You can also represent with a concave lens also. I'm taking a concave lens. So okay, so parallel beam of light, I'm taking a symmetrical axis. So I'm representing the bending of light from this symmetrical axis. Actually light rays are bending at these two surfaces. For my convenience, I'm representing the bending at this symmetrical axis. This is a parallel beam of light. So okay, so after refraction, so light rays appears to be diverse. They refract like this. Okay, so they diverge like this. Okay, so the light rays diverges from the concave lens like this. So but they appears to be coming from this point. So that point is called as the focus. This is a focus. So the amount of divergence, this is the divergence. The amount of divergence or convergence represented by one physical quantity, that is the power of the lens. So it depends on what quantity, the focal length. Smaller the focal length, greater will be the larger will be the stronger will be the refracting power of the lens. Now we'll derive this expression of refracting power. We'll derive P equals to 1 by F in this class. Now let us take a concave lens. No, not concave. No, I'm taking a convex lens. Let us take a convex lens, and this is the principal axis of this lens. This is the optic center. Now take a single ray of light which is parallel to the principal axis. Now I'm taking a symmetrical axis. I'm representing the bending of this light ray from this symmetrical axis only, but actually the light ray bends at these two surfaces. For my convenience, I'm representing the bending from this symmetric axis, uh, and light bends and reaches a point on the principal axis. This is the focus. Okay. And physically it is defined as mathematically, so it is expressed as P equals to F, and it is defined as the amount of bending. What this refracting power represents? The amount of bending. So let us extend this parallel ray of light in a forward direction. So this represents the angle by which the incident ray bends. Okay, so and this by geometry we can also represent this delta. Okay, so it is defined as the refracting power. Our power is defined as power of a lens is defined as by the definition the angle, the it is defined as the tangent of the angle by which it converges or diverges the light falling on it at a unit distance from the optic center. Okay, so power of a lens, it is the tangent of the angle. So this is the angle by which it bends. So it was bent by this lens. Okay, and how can you define it mathematically? Tangent of the angle. So power of a lens is represented as P equals to tangent of the angle by which it converges. Since it is a convex lens, it converges the light falling on it at a unity distance from this optic center. P is equals to tan delta. So I'm taking a right angle triangle here. This is F. Let it be M, and this is O. And from the triangles we can write tan delta is equals to OM by OF. That implies, what is tan delta? The tan delta is equals to, we can write it as tan delta is equals to OM, nothing but the height at which it incidents. So let H is the height of the light ray from this optic center. So we can write H by OF is a focal length. Here distance between optic center and focus, this is a focal length of this lens. Now we can write tan delta as tan delta is equals to H by M. By the definition, we can write P equals to tan delta equals to H by F, and if it incident at a unit distance, if H is equals to 1 unit, then we can write it as P is equals to tan delta is equals to 1 by F. So we can write it as P is equals to 1 by F. This is the relation between the refracting power and focal length of the lens. Okay, so this is about the refracting power. And the SI unit, the SI unit of refracting power is diopter. Okay, represented by symbol D. So 1 diopter is equals to 1 meter inverse. Since P is equals to 1 by F, okay, 1 diopter is equals to 1 by 1 meter. Okay, this is the unit of diopter. Diopter are 1 meter inverse. For example, when you go to the optician, optic eye doctor, ophthalmologist, or optician. If you have any eye defect, you have defect in the vision. For example, if the doctor suggested you a lens of refracting power, P is equals to 2 diopter. So what will be the focal length of the lens? Okay, so here positive represents uh, so what this positive represents we will see here. So what is a focal length? We have a relation between focal length and the refracting power. P is equals to 1 by f. So that implies f is equals to 1 by 2. That is equals to f is equals to 0.5 meters. Okay, so f should be actually this is the expression of power will be in diopters when only the focal length is in meters. So when we are using power in diopter, definitely we will get focal in terms of meters. Okay, not in centimeters. Why? Because 1 d is equals to 1 meter inverse. When you put the value of power in diopters, definitely we will get focal length in meters only. So when you convert into focal centimeters, what do you get? You will get 50 centimeters. This is a lens we need to use to correct the vision, which was prescribed by optician, and this is we got positive. So convex for convex lens for convex lens focal length is focal length is positive. So definitely we got a focal length of we got focal length positive focal length. Definitely the lens which was prescribed by the doctor is the convex lens. Okay. Now another doctor for another person suggesting a power of minus 4 diopters. What will be the focal length of? We need to find what is the focal, what lens is used to correct the vision, and what is the magnitude of the focal length required. So f is equals to 1 by p. We can write like this. So f is equals to 1 by p. F equals to 1 by minus 4, and f is equals to and what do you get? Minus 0.25 so meters, and you will get f is equals to, and will get f is equals to in centimeters minus 25 centimeters. So this is the required focal length. Your negative sign represents the lens is concave. Okay, so this is about the power of the lens. Now we'll derive uh, so now we'll discuss one more topic, that is combination of lenses. combination of lenses combination of combination of two thin lenses in contact. Combination of two thin lenses in contact. So this is the next topic. So let us take let us consider two thin lenses of focal length f1 and f2. I am taking two thin lenses. They are kept in contact. So f1 and f2. Okay, these are two very thin lenses, and they have common principal. Sorry, this is a common principal axis. So L1 and L2 are the two lenses having focal lengths f1 and f2. So their refracting powers are different. Okay, so when you place an object at this position, and the image will be obtained on the other side. So here let us place an object O on the principal axis. I'm taking two light rays from this object. So one is going to strike the lens like here, and this is symmetric. I want to represent the bending. I want to represent the bending from the symmetric axis. Actually, the light bends from these two positions. Okay, two surfaces. Okay. Now here, if there is no second surface, if there is uh, no second lens, it would bend like this and meet and reach the principal axis at this position. But because of the secondary lens, once again the refraction takes place here. Once again the refraction takes place, light finally reaches this position. Okay, so here we get the final image. This is the object distance. For my convenience, I want to measure up. I want to assume one point. The optic centers of these two coincide at this point. So why? Because where they are very thin. So let us represent the image, the final image distance. This is V. Finally, we are getting the image here. This is optic center. Okay, and this is the image due to the second image due to the first lens. This I will represent with another letter V1. Okay, now I'll apply, since I'm taking lenses, so I'll use lens formula to find the combined length, combined focal length of the given combination. Now what is our aim in this topic? I want to find out the combined focal length of this combination. Okay, right. Now uh, see here, for first lens, for first lens apply the lens formula. For first lens, this is a light ray. Once again they'll meet here, we'll get the image, final image, and this is the image due to only first lens, I dash, let it be. Okay, so for first lens, the object distance for the first lens, u is equals to, object distance is u. For the first lens, u is the distance object distance. And for the second lens, and image distance, first next I'll write image distance. V1 is the image distance. V1 is the image distance. Okay. Why? Because if there is no second lens, so the light will reach the point I dash, not I. So okay, so that is why that distance will be V1 from the optic center. Now now I'm writing the lens formula, and by using lens formula, 1 by f1 is the focal length of the first lens, 1 by fn is equals to 1 by v1 image distance, 1 by minus 1 by u. This is for first lens. Okay, and next for second lens, for second lens, so what do you get? For second lens, what is the object? The image of first lens will act as an object to the second lens. So this is a virtual image. So what is the object distance here? What is the object distance for the second lens? So V1 is the object distance, and what we get here, so 1 by f2 is equals to, here we will get 1 by f2 is equals to 1 by image distance, 1 by v minus 1 by v1. V1 is so object distance for the second lens. So here I'll write one point. So image of first lens first lens acts as an object to the second second lens object to the second lens. That is why image distance of the second lens is v1, distance is v1. Okay, now let it be another equation. So let it be equation number 1, and this is equation number 2. Equation number 1 and 2. Now add these equations 1 and 2. What do you get? So add equations 1 and 2. We'll get 1 by LHS is 1 by f1 plus 1 by f2 is equals to 1 by v 1 by u, sorry, 1 by v1 minus 1 by u plus 1 by v minus 1 by v1. Now these two cancel out, and we will get 1 by f1 plus 1 by f2 is equals to 1 by v minus 1 by u. Okay, so here the combination of two lenses, so we will add the if the combination acts as a single lens of focal length f, then the relation between focal length and image and object distance can be written as 1 by f equals to 1 by v minus 1 by u. So we can write the final expression as, so 1 by f is equals to 1 by f1 plus 1 by f2. Okay, when two thin lenses kept in contact on the principal axis, then the reciprocal of the effective focal length is the sum of the reciprocals of individual lenses. This is the expression for combined focal length. So from the previous topic, we know that P is equals to 1 by f. Okay, that implies P1 is equals to 1 by f1 and P2 is equals to 1 by f2. So we can write this expression as, the above expression as, in terms of P as, P is equals to P1 plus P2. This is the combined refracting power, net refracting power of the combination. Okay, now if you have number of lenses, let f1 comma f2 comma f3 and so on, fn are the focal length of the combination of n lenses, then we have expression for combined focal length as 1 by f is equals to 1 by f1 plus 1 by f2 plus 1 by f3 plus and so on plus 1 by fn. Similarly, the expression in terms of power equals to P equals to P1 plus P2 plus P3 plus and so on plus Pn. Next, for example, M1 is the magnification of first lens, M2 is the magnification of second lens, M3 is the magnification of third lens. So the magnification of the combined magnification can be written as M1 into M2 into M3 into M4 and so on Mn. Okay, so this is about the refracting power for the combination of two thin lenses in contact. Okay, so briefly I'll recall this topic. So what is the power of a lens? It is a measure of convergence or divergence of a lens, and it depends upon the focal length of the lens. It is the reciprocal of the focal length of the lens. So and mathematically it is defined as tangent of the angle by which It converges or diverges the light rays incident uh, on it at a unit distance from the optic center. By using geometry, we can find the power of a lens as P is equal to tan delta is equals to H by F. When it incident at a unit distance from the optic center, we can write 1 in place of H. So we'll get P equals to 1 by F. This is the expression of power of a lens. And SI unit of power is diopters. And the 1 diopter is equals to 1 by 1 meter, nothing but 1 by 1 meter inverse. Let us take an example. We have taken one example for the length of diopter 2, the focal length, we will get it as 0.5 meters or 50 centimeter. The positive sign represents the lens is convex. And if you take another example whose refracting power is minus 4 diopters, we will get focal length as minus 25 centimeter. A negative sign represents the lens is concave. If you take two thin lenses in contact, if two thin lenses of focal length f1 and f2 are in contact, mm, we need to find the expression for combined focal length. So if is the combined focal length f1 and f2 are the individual focal lengths, we have taken an object placed on the principal axis, and the image of that object will be observed on the other side. So here I1, I dash and I are the images due to first and the combination, first lens and the combination of lenses. For the first, if you have only for first lens, mm, if there is, imagine there is no second lens, the object distance will be u and image will be formed at I dash. So corresponding lens formula will be 1 by f1 is equals to 1 by v1 minus 1 by u. Okay, but actually what happens, because of the second lens, the image will be observed at I not at I dash. That is why the final image distance will be v. So actually it is not for the second lens, for the combination. No, for the second lens only, no problem. For the second lens, 1 by ft is equals to 1 by v. So we are getting image at v. And remember one point here: the image of first lens will act as object to the second lens. That is why in place of object distance, I'm writing v1 here. I'm writing v1 here. Okay, so v1, right? Next expression. Sorry. Right. If you add these two equations, now I'm adding equations 1 and 2. Adding equations 1 and 2 will get uh, expression in terms of 1 by f1 plus 1 by f2 equals to 1 by v minus 1 by u. If the combination acts as a single lens of focal length f, then we can write that expression of 1 by f equals to 1 by v minus 1 by u. And if you combine these two expressions, above expression will get 1 by f equals to 1 by f1 plus 1 by f2, and finally if you write the same expression in terms of power, you will get P equals to P1 plus P2. For the combination of lenses, we can write this expression as 1 by F1 equals 1 by F equals 1 by F1 plus 1 by F2 and so on. In terms of refracting force, we can write it as P equals to P1 plus P2 plus P3 and so on. If the magnification, M1 is the magnification of first lens, M2 is the magnification of second lens, so on, Mn is the magnification of nth lens, and total magnification of the combination can be written as the product of the individual magnifications of the lenses. Okay, this is about the combination of lenses. Thank you.